Okay, in this video we're going to continue where we left off from the previous videos. We're continuing on our 2D line in the 2D part of GeoThrust. And the previous videos we built a project and we picked some first breaks and then we took a quick look at the first breaks. Now in this video we're going to build an initial model, run travel time tomography, and calculate some statics. So we will continue on in the T-time module, which stands for travel time. We looked at this previously. In this module, we are able to remove some poor picks, remove some outliers, which we did. But now we're going to build an initial model. So this icon here will show us the same display, shows all of the picks here. But now we're ready to actually build a 3-layer model, perhaps, or whatever number of layers we want. I'll click on that triangle to open up the window. And now I'm going to make my first mouse click somewhere other than 0. This will be the end of the first refractor. I can make another mouse click there and another mouse click up there if I like, and I have built a 3-layer model. If I decide I want to change that, I can hit the backspace key, and I'll actually remove all those points. I'll try that again. One mouse click here, another mouse click there, and another mouse click somewhere up here. I right-click to complete that. It tells me the velocities I've chosen. I'm okay with that, and I can accept that. And I'm going to build an initial model with these dimensions. The grid size, the default grid size is 5 meters in this case. I'm going to hit apply. And now I've output a file that I can use as the starting velocity model in order to run some iterations of travel time tomography. I'll close that. I can close that. Since I've built an initial model, we can see that the T-time module has turned green. Go into the tomo module, and it's filled in the defaults for me. The initial model I had, the travel time file with my first break picks. Let's say run 10 iterations, smoothing control 1, inversion grid factor 1, and 1. So these inversion grid factors are actually multipliers of the original cell size that will be used when doing the velocity updating. So in my case, I had a 5 meter by 5 meter grid cell in the initial model that I built. And if I take a look in Picker here, information, the SIGY information, it'll bring up this summary just to remind myself what the shot and receiver interval of this data set are. So my receiver interval is 20, my shot interval is 40. So basically, since I have a 20 meter receiver interval, I very likely would like to put a grid factor of at least 4 here, perhaps larger because the shot interval is larger. But at the very least, I want to put a larger effective cell for when I'm doing the velocity updating. So again, this will use a 4 times 5, so 20 meter cell for the velocity updating, 20 meter by 5 meter in this case for doing the velocity updating, whereas it will use the original 5 meter cell size for doing the ray tracing, trophy inversion. So these are probably okay. I'm going to select some nodes, the machines I want to run this job on. I've selected a couple of them, and I'll use 20 cores per node to make this run a bit faster. For now, I will start running this. And this may take a few minutes, so I will, once I'm convinced that this is starting, I will stop the video and then continue on once it's complete. Okay, we can now see that the tomography is completed. It's actually run 10 iterations. We can see the misfit went up a little bit in the after the first iteration, but that may be okay. Bottom line is we would like the RMS misfit of all of the shots to decrease after each iteration. So we can see that this is gradually decreasing. We probably would have wanted to run more iterations because this is still decreasing. But in this case, we'll take a look at the velocity model and we'll go ahead and calculate statics anyway. The middle display here is the RMS misfit per shot, so along the line. Each shot will have an overall average misfit, the difference between the true first break fix and the synthetic fix generated from the velocity model. The panel here is the initial velocity model, and the bottom panel is the final velocity model. These get updated after each iteration. Of course, the initial model stays the same, but the misfit gets updated after each iteration, and we can take a look at that whenever we like. There are some advanced settings under options where you could change the offset range that you use or limit the velocities that could be used. Left and right velocity extension range. This is a good parameter to keep in mind. This means that 400 meters from the first and last shot, the velocity model will be extrapolated outwards. So you may find a time that you want to, basically, you don't want to extend the velocities outward from so far in from the line. So you may find that you want to change that to something smaller so that you don't have as much of the velocity model extrapolated at the edges. It may be a good idea to run a first job just to take a look at the velocity model and see what it looks like. Another option you may want to choose is the extend refractor velocity. That will just ensure that the velocities always increase with depth. If you have the bottom part of your velocity model that you can't update because the rays don't penetrate there, you may end up with the initial velocity model left over because it was never updated. And so you may choose to use extend refractor velocity to basically end up with a nicer looking model that does not have slow velocities underneath, just simply because it never got updated. For now, we will take a look at our velocity model. In View M for View Model, I can turn on the geometry by this icon here. I can see the shots and receivers. The velocity range on the left, 1,000 to 2,500. The ray density can be displayed here. So this tells us where we've actually penetrated through the model with our ray tracing. So we can see that we don't have rays going off the bottom of the model. That's good. And we also do not have a big part of the model that does not get updated. So this type of ray density display seems reasonable. This gives us an idea how far down we may want to choose to include as our weathering layer. We can go back to the velocity model by this icon, Display Model. And what we want to do now, we see that we have a reasonable velocity model. We also saw the misfit here. What we'd like to do as well as a QC, we'll go back to Picker, and we will overlay the travel time. And we will overlay the synthetic travel time that has the same name as our velocity model. And that's got underscore SYN for synthetic. And now we will see in blue, once it's finished loading, the synthetic travel time pics that are generated from the velocity model. So in red, we have our real first break pics. In blue, once they are loaded here, we will see the synthetic first breaks that are generated from ray tracing through the model. So you can see here in blue we have some synthetic pics, and the difference between those, red and blue, will be the misfit. We can see also that here near the beginning of the line, the synthetic pics do not extend to these receivers on this side, and that's simply because the synthetic does not get generated beyond the first and last shot. If we go to a shot here closer to the middle, we'll see how well the blue synthetics match the true first break pics in red. So this is always a good QC to make sure that you can see that there's a good fit between the true pics and the synthetic pics. So if you're satisfied that you've got a reasonable looking overlay and you don't need to run any more iterations or adjust any pics, you can proceed forward to calculate statics. So that's what we'll do now. So we need to choose a floating datum and an intermediate datum, basically to define where our weathering layer is. So to define a floating datum, we're going to use a smooth version of the topography. So I'm going to turn on the geometry, and the icon beside this will allow me to build a layer from the receivers. So I'll do that. So that's building a layer along the topography. I can choose to smooth that with this icon here, smooth layer, and then by clicking on the layer, that will apply some smoothing to it. So there's not a lot of topography change on this, so I'll just smooth that slightly. Now I want to choose a base of the weathering layer essentially, and I'll call that my intermediate datum. Before I do that, I'll point out we can see that the model has been extrapolated to the left here and extrapolated to the right, and this extrapolation is occurring 400 meters from the last shot and 400 meters from the first shot. So as I mentioned earlier, you may want to change that default so that it does not get extrapolated from quite as far out. And if you would like to extrapolate this further, you could also you could actually switch the order of the travel time, but that will be the topic of another article. Basically, we've got our floating datum. Now let's choose an intermediate datum. For 2D, we could simply build a layer if we want with this icon here. Build layer, and I could simply mouse click and choose some. When I got to the edge, I could right mouse click to complete that layer. I could choose that as my intermediate datum, or I could modify points there or move the layer. Let's say move layer, I click on that icon, and then I can grab this layer and move it up or down. I could also delete this layer. And let's try using this icon here to build an isovelocity. So I can find some layer that maybe I like as, okay, so I clicked here in the velocity model, and maybe I'll say a round number 2000, and if I hit apply there, that will draw that layer at that constant 2000 meters per second velocity. I can see in this case that that's not very reliable, so let's try something at 1800. That seems a little more realistic. Let's see what 1900 looks like. Okay, so bottom line is this one is not any good, so I'll delete that layer. And we could debate on the usefulness of these lower two. Let me get rid of this one. And I think in this case, I'm going to actually build a layer. I'll go back to building a layer. What I could also do, if I want, I could actually copy this topography, and I could have a constant thickness layer. So I'll copy and move. So I'm going to click on that icon. I clicked on the topography layer, and I drag this down, and I'll move it down to there. And basically, I'm going to use that as my intermediate datum. Basically, I have a weathering layer and I have constant thickness. Again, this is more for demonstration purposes. So I will use this as my floating datum, and this is my intermediate datum. And I'm going to save that, and then what I'm going to do, I'm going to calculate statics that move from the true shot receiver locations down through the velocity model using the velocities from the model down to the intermediate datum, and then I will go back up to my floating datum using the replacement velocity. So then I will have the static correction to move everything to the floating datum. And later on in the processing, we'll be doing our NMO from floating datum and our migration from floating datum. So I will save layer, and that will save the two layers in one file, and the default name is going to be the project name _01.lay. So I will close this now, and I'm ready to calculate some statics. I'll go to the stats module. On the left here, the first one is tomo statics. So it grabs the default tomo model, so the highest number that we have there, 01. The travel time file, there's an all file, and that's generated when we export the pics, and that's got all shots and receivers in it. regardless of whether or not they have any first breaks picked on them. So you may have some noisy shots or noisy receivers that you didn't pick any first breaks on, but you still want to calculate a static for them. So the velocity model, the travel time file, basically the geometry, and basically we're going to put the same layer file, which is one we just picked. It has the floating and the intermediate datum in it. So we'll define the intermediate datum. Now we'll define the floating datum. It turns out to be in the same file. And the default replacement velocity will be an average along the intermediate datum. And so in this case, 1900 seems okay. And we're going to output a statics file with this default name here. I'm going to click apply. And I've calculated a tomo static. So this is my long wavelength static to move everything to the floating datum. Now I'm going to calculate a travel time, a refraction-based residual. So I have two different options here, the database residuals and model-based residuals. The database is calculated by applying the long wavelength statics we just applied, or we just calculated, and then applying a linear move out or a reduction velocity using this velocity. Applies those both to the travel times, and then it applies some smoothing. The difference between the smooth and unsmoothed versions of that travel time file will be decomposed into shot and receiver refraction-based residuals. So that would be the database residuals. So in our case, we have our best first break picks. We have the statics that we just generated and that we are viewing here. We'll do 10 iterations of decomposing into the residual statics. This velocity of 2000 seems like a reasonable velocity to use to flatten the travel time file. We'll stay a little bit away from the direct arrivals. We'll use the picks between 500 and 3000 meters of offset, and we'll leave the we'll put in the receiver spacing of 20 and shot spacing of 40. These will affect the smoothers that are applied to calculate the difference between smooth and unsmooth. So we'll apply that, and it's going through and it's generating these refraction-based residuals. Again, these are quite small, centered around 0. So that's the database residuals. We'll also calculate model-based residuals. This is an alternative method. So what you should do is take a look at both results and compare them on your data and see which results you like better and use the best results, basically. The model-based is simply going to look at the difference between the misfit. Basically, it's going to decompose the misfit into shot and receiver residuals. So the difference between the true first break picks and the model, the synthetic first break picks, will be decomposed into shot and receiver residuals. So here is our first break picks. Now we're going to input the synthetic travel time file that was generated from that velocity model. And we're going to use the same offset range and same number of iterations. And this time we'll call it 0.2, and we'll apply that. We're calculating model-based residuals. So we can see that these are fairly small as well, centered around 0. We'll close that. And now we could take a look at these actually applied on the data to see which one we like better. For now, we'll close that. We'll close this window there. So now we've calculated our statics. So let's just take a quick look at them applied to our data to see whether they seem reasonable. So we're going to open up the prep module, and under PS for processing sequence, we can get rid of this previous sequence. Let's maybe just, this is just going to take a look at the statics, so we'll apply an AGC, and we'll apply statics. we'll input our statics file. So the tomo 01 here is the long wavelength static. We're going to input our datum file, although it's not necessary for this when we're just viewing the statics. We'll input that just as good practice, and we'll input our replacement velocity. So the reason we want to input this datum file is typically when we are applying statics to our data, we need to populate the SIG-Y trace header with where this data is now being referenced to. So when we're applying statics, we'll apply the static and we'll tell the program basically where the floating datum that this data is now hung from is located. So this will populate bytes 53 and 57 in the SIG-Y, in the output SIG-Y, with the floating datum. So for the purpose of here where we're just viewing the results of the statics on the data, we wouldn't necessarily need to do that. That's why this has an asterisk, meaning it's optional. But it's good practice to do that so that if you are grabbing this module later, then you'll remember to do it. The replacement velocity will be put into the trace header as well, and will be used as it will be grabbed when we're looking at the running stack cube to run velocities. Okay, so this will apply the long wavelength static. So we can copy this, and then we can change the statics file for the second application to the database residual. And we'll just take a look at those. In this case, we're not going to output anything. We're just going to look at this interactively. So I'll hit apply to save this flow. And we can use the arrow up here or the arrow on the keyboard. We'll go forward to the next step in the processing sequence. So that's just applying an AGC. And then we'll go forward to the first statics application. So that's applying the long wavelength static. So without the static, I went back. With the static, and now we'll apply the residuals. So of course on this shot it is quite kind of difficult to tell. I'll go forward to the 10th shot, for example, just to see. Go forward, apply an AGC. Now we'll apply the long wavelength static, then we'll apply the residual. So without the residuals and with, we should see a little bit more continuity with the application of the statics. We could also go ahead and compare the effect of the model-based residuals. We can actually change the parameters up in the boxes here. I could actually go back and hit enter the second statics file, which was the model-based residuals, and I hit enter, and we can see that it's updated that, and now it's applying the model-based residual. So I could go back, so that's without any residuals, and then this is with the model-based residuals. So here you can take a look at the application of the statics on an individual shot and determine which statics you like best. And that's the extent of this video. We'll continue on in another video after this.